Okay, so we'll be talking about this particular question over here from mass spectrum, mass spectrometry. It says that the mass spectrum of a compound shows M+2 ion peak, that is about 4% of M plus peak, right? And this indicates that the compound has 1. What is over here, right? So now you should know that first of all, it is said that the compound has 1. Okay, one of the thing is present over here. Now you should know about few values, right? Especially about your halogens. So if fluorine is over there, fluorine does not have any other isotope, any other stable isotope. So fluorine is only present in 19F. So it will not give you M+2 peak, right? So it will just give you a M peak. It will not give you M+2 peak. So you should remember this thing, okay? So fluorine does not give you M+2 peak. So that is cancelled out. Now talking about bromine. So bromine has 2 isotopes. So both of these isotope has like the intensity ratio of these isotope is 1:1. Okay, so it won't be 4% of that. It will be like 100% of the other one. Okay, so it's quite similar to that. So if you take one of the peak to be 100, so the other one will be 100%. So it will be said that bromine will give you 2 peaks, M+2 peak with intensity ratio of 100%. So that is also not going to be the correct one for this particular question. So it's wrong. Now talking about chlorine, so chlorine exists in 2 isotopes, you know about it, chlorine 35 and chlorine 37, and the intensity ratio of these is 3:1. That means 3 times of this chlorine is like that. So if you take one of that as 100%, so other will be 1/3 of that. That means 30% of that. Okay, so that means if this is 100%, so the other one will be about 33%. Okay, that is not in the given question. It's around 4%. So that is also not going to be the correct one. So if you just cross down if you just cancel down all the odd ones, you will get the answer. The answer is sulfur. Sulfur actually exists in 3 isotopes. Your 32 sulfur, you have 33 sulfur, and you have 34 sulfur. The intensity ratio, if you take 32 sulfur as 100%, then you have around 70% of this 33%, and the rest one, that is 4%. That will be around 4% of that. Okay, so this is your M peak and this is your M+2 peak. So remember this thing, that for the M+2 peak of your sulfur, it's around 4%. So this sulfur is going to be the correct option for this, right? So it was an easy question. Now talking about this particular question over here, question number 41, it says that okay. So the question number 41 says that the number of signals observed in the carbon 13 NMR spectrum of the following compound. So here is the compound given to you. Now it was very simple question, very easy question of 2 marks. You just have to visualize this compound. You can just make a plane out of this molecule. If you just bisect this molecule in between of these these 2 oxygen containing groups. So if you apply a plane like this, so basically what it will happen, that this particular carbon will be like it will be equivalent to this particular carbon, the carbonyl carbons. The rest will be like B. I'm just numbering them right like that. Then you will be having C for that, D for that, E for that, and F for that. So you will be having 6 different types of carbon. So option number 3 will be your correct choice for this question. It was very simple. You just have to visualize the compound. Okay, you just have to apply the plane. If your molecule is something like this, so if your molecule is something like this, you can apply a plane which will pass through these bonds, and which will bisect this carbon will be reflected, this carbon will be reflected, this carbon, and these 4 carbon will lie on the plane. So that's how you will get 6 carbons in this particular case, right? Okay, let's take the other questions. Fine, so we'll try to do this particular question over here. And the question says that the compound shows following spectral data. You have given with the data of proton NMR, and it's given few things which you need to know over here, which are highlighted over here. Is this, that is, you get 4.0, like chemical shift at 4.0 due to broad singlet, and because of 2 hydrogens, and that too is a D2 exchangeable. Now D2 exchangeable are only 2 kind of protons. Either that will be NH2 proton or OH proton. So generally, like since these are 2 protons and they are giving you broad singlet, so they will be NH2 proton, okay, attached to a carbon which does not have any hydrogen at it. Fine. Now you need to see the J values. Okay, so over here these J values, where J is equals to 8 Hertz, this particular one and this particular one, both are very near to each other, 7.9 and 6.6 chemical shift, and both are like they are coupling like with each other, because J is equals to 8 hertz is for both of them, and the both of them are because of 2 hydrogens. So that means it shows you that your product is actually your para substituted. Okay, so this is giving you that your product is actually para substituted. So para substituted product. Okay, understood this thing? Why? Because these 4 protons are actually coupled with each other. So that 4 protons cannot get coupled over here if it is not para substituted. Okay, so they cannot couple with each other. So that can only be possible in option number 1 or in option number 2. Okay, so we cannot say that which one is the correct one. Either option 1 is correct or option 2 is correct. Now we need to see that the proton which is attached to, like, okay, so we need to see this proton. Okay, this proton will give you the value for that. So fine. So that means in order to understand this, the next thing is given to you, that is your mass spectrum. Okay, so if you try to make the structure of the compound, if you try to make the structure of this whole compound, so basically if I take second one to be the correct structure and if I try to make it up, so this will look something like this. So I have a phenyl ring over here, and I have double bond ONH2. Okay, and over here I am having oxygen, and then I am having this. Okay, fine. So that means I have, okay, so this is my option number 2, and if I do for option number 1, so my option number 1 is this. Okay, so this is my option number 1 where I have NH2 and I have C double bond O and then this. Okay, now I can say that in option number 1 I have gamma proton, and this can be seen over here like this. This is your alpha to the carbonyl group, this is beta, and this is gamma. Whereas in the option number 2, this is your option number 2, this is your option number 1. So in option number 2, that is not over here. So McLafferty rearrangement is only possible in option number 1. Okay, so McLafferty rearrangement is possible over here. So that will happen actually in option number 1, and because your overall mass is your 165 for the compound, and after this McLafferty, and the McLafferty will be done, in that case you will be getting certain thing like this. Okay, so you will be getting, so you'll get something like this, which will have M by Z of 137. That is also given in the mass by charge given, like the mass spectrometry given data, right? And the other possible things will be when you do alpha cleavage of this. So if it undergoes alpha cleavage, so it can undergo alpha cleavage and it will give you this. So this is the product which you get after alpha cleavage, and along with that you will get a fragment like this. Okay, so your M by Z for this is 120. That is also given over here. And how you will get 90? 90 you will get if this group leaves this out, right? So if you have minus CO, CO leaves this, so you will be getting some, like the last fragment which is possible over here will be this NH2. So, and also positive charge over it. So this will have M by Z of 92. That is also satisfied by this. So the only option which satisfies all your NMR data and also your also your mass data, that is your option number 1. So that is going to be the correct one. And for your reference, I am just going to tell you that what will be the probable chemical shift values for all of them. Okay. So this is going to be the overall proton, the values of your proton and NMR chemical shift for different hydrogens. These are all mentioned along with them. Okay, so I hope this will be helpful. So now let's take some more questions. Okay, so let's take this question over here. Now, although this question is not exactly from your organic spectroscopy, but yet I have taken it because there were a lot of confusion over here in this question from you guys. So I thought that I should include this in this particular video. So the question says that consider the nature of solvent in column 1 and the corresponding lambda max for I2 and the various solvent given in column 2. Okay, so it is given that I2 in vapor phase that has lambda max of 520 nanometers. So match column 1 with column 2. So how to match it? It's very simple actually. We should know about what kind of transition is actually taking place in your iodine. Okay, so you should know about this. That's all. So that is the basic thing which you should know in order to attempt this question. So iodine is a kind of halogen, right? That too a very big in size, and when you form two iodine are actually formed with the help of that sigma bond, right? And there are certain there are certain non-bonding electrons as well, but usually the bond between the two iodine is sigma, right? So when the transition takes place, actually it's actually between your sigma star, okay? It's actually between your so it's actually between your sigma star orbital. Fine. So the transition actually is between your pi star and your sigma star orbital of iodine. That's what the transition takes place, and the lambda max for that you have as 520 nanometer. Okay, so that's the value of your lambda maxes, right? So now if you take a non-donor ligand, that means there is nothing to donate in that. So if it is dissolved in a non-donor ligand, so there will be no effect in the energy of pi star and sigma star. Okay, so the energy of pi star and sigma star will not be changed. So in case of non-donor, it will be same. That is, the lambda max will remain same. That is 520 nanometer. So actually your non-donor will be matched with this 520. Okay, so A is matched with 1. That's what I am writing over here. Now, what will be the effect of donor kind of ligand? Okay, so the solvent donor orbital. Okay, remember this thing, whatever I am writing. So solvent donor orbitals. Okay, now solvent donor orbital, they interact, okay, with the pi star orbital. Sorry, with the sigma star orbital. So solvent donor orbital interacts with sigma star orbital of your iodine molecule, and the result is that your LUMO becomes lower in that energy. So basically, if I write down the energy order, so what will happen actually when the donor ligand comes in, when the solvent donor ligand comes in, the energy becomes higher. Okay, the energy difference between the sigma star and pi star becomes higher. So as I'll just write down over here, just remember this thing. So as solvent donor ability, okay, increases, the energy difference between sigma star and pi star increases. So that means if the solvent donor ability increases, the energy difference between sigma star and pi star orbital increases, and your lambda max will decrease, right? So if I write down the order of your energy for the different like solvent donor over here, so order of energy will be, if I write it down over here, so the energy will be like this. So you will be having like your strong donor will make highest energy difference, right? And then comes your weak donor. Remember, these strong and weak donor, they generally interact with the pi star orbital. So that's sigma star orbital. So that's why it is. And then comes your pi electron donor. Okay, so pi electron donor, they will come in the least position. So this is the order of energy. So what will be the order of your wavelength? So you know that energy and wavelength are inversely proportional. So order of your lambda max will be like this. So your strong donor will give you lowest lambda max. So the lowest lambda max over here is 360, right? So your strong donor will give you around 360. Then comes your weak donor, it will give you little higher energy. So yeah, so your weak donor will give you around 450, right? And your pi donor ligand will give you little more higher energy. Little more higher lambda max. That is around 500. So this is how they will be matched. So B will be matched with third, okay, C will be matched with fourth, and D will be matched with second. So like that, your option number 3 becomes your correct choice. So in this way, you have to solve this question. Okay, remember this thing, that whenever you have more solvent donor ability, the energy difference between the transition energy increases. This happens with all the cases. Okay, if you, instead of iodine, if you have some other like gas given over here, then also or some other solvent given over here, the same thing will happen over here. So when you increase the donor ability, the energy difference also increases and the lambda max decreases. So that's how it has to be done. Fine. So let's take some other questions now. Now this particular question is also a part of your organic spectroscopy, which was asked in your CSIR June 2018 exam for 4 marks. It says that the correct match of the protons in column A with the proton NMR chemical shift in column B for the product of the following reaction is. Now you need to know about the formation of this. Okay, so here the concept of homoaromaticity comes into play, and I have made a video on it on my Unacademy profile. So there I have explained what is aromaticity, what is homoaromaticity and all. So if you are not following me over there, you should follow over there, because there are a lot of informative videos available for CSIR net preparation. So fine, let's coming back to this question. This is how it will be formed. Okay, so I'll just write down the reaction, which kind of reaction it will undergo. So this is a compound which is a non-aromatic compound. Now once it takes a proton, it forms a 7-membered resonating ring. Okay, so something kind of this. Okay, so I'll just show you that how it will look. So you'll be having a positive charge over here and 2 protons over here. Now this is the proton, this is the sp3 habit carbon, which will go out of the plane in order to make the other 7 carbon to be in the resonance and to form a aromatic ring kind of thing. Okay, so that's how this particular structure comes into play. Now talking about these 2 proton, HA and HB. So since this is the ring current, this is the aromatic ring current, and you know that the thing which comes into this under this aromatic ring current, that becomes highly shielded. Okay, now this HB will become very much highly shielded due to the ring current of this aromatic ring. So that's why this will give you very negative like chemical shift. Now since these 2 proton HA and HB, both of them are on sp3 carbon, so there will be a very huge chemical shift difference. Why? Because one of them will be towards this ring current, okay, and the other one will be away from it. So both of them will have very much high difference in chemical shift. So your HB will have a chemical shift of minus 0.3 and HA will have a chemical shift of 5.1. Okay, so this is what the value you will usually get. Now talking about your H1 and H7. So basically your H1, so fine. So basically talking about your H1 and H7, they are relatively more shielded compared to the other one, that 2, 3, 4, 5 and 6. 5 and 6. Okay, so compared to them, your H1 and H7 are relatively more shielded, and thus they will be having a relatively lower chemical shift. That means that their chemical shift will be relatively upfield. Okay, so that's why your 1 and 7 will have a value around 6.4. Okay, and your 2 to 6 they will have a value of 8.5. So your option number 1 becomes your correct choice. So just you need to know that where your proton is shielded and where it is de-shielded. That's all you need to know in order to solve this particular question. Fine. So I hope that this was clear to you guys. If you have any doubt, you can ask in the comment section. Now talking about this particular question, here you have to assign the IR spectra, order of your IR spectra, IR stretching frequency in the given carbonyl compound. Now you can see that for compound B there is no conjugation with the carbonyl group, right? There is no double bond in the conjugation with carbonyl group. Remember this, that conjugation with CO decreases frequency. Okay, decreases stretching frequency. So if there is a conjugation in with your carbonyl group, the frequency decreases. That means frequency of A and C will be lower than that of B. So B will have highest frequency. Now option number 2 and 4 can be easily cancelled out. Either your option 1 is correct or your option 3 is correct. Any of these can be your correct option. Now we have to assign between A and C. So when you have to check between A and C, so how you have to do, your trans conjugation is much more easier and favorable than your cis conjugation. So that means the conjugation effect or the plus M effect which is happening in option A, that is relatively much more stronger than that of C. Okay, and if the conjugation is more, then the frequency will be less for that. So that means A will have lower frequency over there, right? So I'll just write down over here. So plus M effect, the order of plus M effect of A is more than C. So that's why your frequency, okay, your carbonyl frequency will be like this. So you will be having C more than A. So this will be the order of carbonyl frequency. Now what will be the total order? So B is most of that. So B, then comes your C, and then comes your A. So option number 3 becomes your correct choice. So like that you can easily get 2 marks. Let's take some more question and see how to solve them. We'll be taking up this question over here. It was asked for 4 marks. It says that the structure of compound displaying the following characteristic spectral data. Okay, your IR is given at 1720 centimeter inverse, and you are given with a different proton NMR question, like proton NMR data, right? Now, it was very debatable question. A lot of discussion was going on in this. So I'll try to make you guys understand in the most easiest way possible. Okay. So first of all, your IR at 1720 centimeter inverse. This actually tells you about a function group, and that function group is your alpha beta unsaturated ester. Okay, so it tells you about alpha beta unsaturated ester. So alpha beta unsaturated ester, so ester is only possible in option 1, 2 and 3, right? So alpha beta unsaturated ester is is over there in option 1, 2 and 3. So these 3 can be correct. Fourth one is not correct. Okay, so fourth one is the wrong answer according to your IR data. Now you need to see that you need to just now tell about the number of proton signals. You just have to look upon to the number of proton signals, and relative to that you can easily tell, right? So over here, this proton over here, this one over here is, this one will give you what? Okay, so just look upon to the splitting pattern and you will get the answer after that. Okay, so I'll just write down the splitting pattern over here. So it will give you a singlet. You will be having 2 protons over here. So these 2 protons will give you so these 2 protons will give you different peaks. Why? Because this hydrogen is in anisotropy of this carbonyl ligand, right? So because of this carbonyl anisotropy of this carbonyl, this proton and this proton will show you different NMR peaks. Similar thing will go for your option number 2 as well. Over here also these 2 protons will show you different peaks due to the anisotropy of that. Okay, and other thing will be same for both of them. The only difference between both of them will be at this particular carbon. Your proton of this particular carbon will give you much higher chemical shift in option number 2 as compared to in option number 1. So in option number 2, this particular proton, which should give you a quadrat, okay, the one which should give you a quadrat will give you at higher peak. So that is what it is given to, that is 4.2. If it would be this one, it would not have given you at 4.2, it would have given you around 2 point something. Okay, so that's why option 1 is not correct. Okay, so this which is giving you a quadrat, that is giving you a little higher value. That means that this particular CH3 group is near to your oxygen. Okay, now this quadrat and this triplet all together, they make that tells you that you have CH2 CH3 somewhere in the group, and this CH2 is attached to a very electronegative group. So that's why it is 4.2. Okay, and this one is 1.1 triplet. So yeah, all the data like IR data and NMR of this particular group is the deciding factor to identify that your correct answer should be your option number 2. So like that you can easily answer this question. Okay, so there was not much on it. Other things you can understand. I'll just make you guys, I'll just draw this molecule and I'll show you that what will be the chemical shift for the different protons over. So these are the different chemical shift values which are indicated over here for all the protons. Now this particular proton is giving you a very higher chemical shift, that is of 6.2. That is because this is in the anisotropy of this carbonyl group. Okay, so it is near to the anisotropy of this, that's why. So your answer should be your option. Fine. Okay, now we'll talk about this particular question over here. It says that the partial spectroscopic data is given below for an organic compound. Okay, and the data shows you that you have 4 signals between 120 to 150 ppm for carbon 13 NMR, and then it shows that you have 2 doublets between 6.8 to 8.5 ppm in the proton NMR spectrum, and the third thing which was given to you was that you get a absorption band at 1724 centimeter inverse. Now see, this kind of question was like CSIR does not give you usually this kind of question, because they give complete NMR data and then they ask the structure of it. This was first time that they have given partial spectroscopic data and they want the structure of it. So the thing become a little more difficult over here to solve. But yeah, I'll try to explain you in the most easiest way possible, right? So in the carbon NMR spectrum is not that much of use over here, but yeah, it will be used. I'll tell you how. So first of all, your IR band will tell you about the functional group. So at 1724, you either get for a ketone or you get for alpha beta unsaturated. ester. Okay, so alpha beta unsaturated ester or ketone gives you around 1724 centimeter inverse, right? Around 1720, like 1700 to 1725. So it is the region for that. So among the following options, if you can see, so option number 1 is cancelled out because it's not alpha beta unsaturated ester yet, and also it's not a ketone. So now your options 2, 3 or 4 can be correct option, right? Now talking about option number 4, so in option number 4, this the double bond or the carbonyl bond is not in conjugation with the double bond, right? So alpha beta unsaturated ketone, it should be like that your carbonyl group should be in resonance or should be in conjugation with a double bond. That is not possible here. That's why it will give you, like, the IR for this will be little higher, and that will be around 1740 centimeter inverse. Okay, so that's the option number 4 will also be not correct. Okay, so remember 1725 is for alpha beta unsaturated ester, and also that is the carbonyl of that ester should be in conjugation with the carbon-carbon double bond. Okay, so now it can be either your alpha beta unsaturated ester of option 2 or a simple ketone of option number 3. Now if you check over here, so now your NMR data will help you to do that. So you are getting two doublets between 6.8 to 8.5. That means that tells you that two doublets. Two doublets means those two protons are of, like, okay. So let's see over here. So this carbon in the option number 3, I'll just write it down over here. So it will give you a doublet because adjacent to it you have one proton. This will also give you a doublet. This will also give you a doublet, and this will also give you a doublet. And this carbon or this proton will be, these two proton will be equivalent, and these two proton will be equivalent to each other, right? So you are getting two doublets over here, and the region will be 6.8 to 8.5 because it's a aromatic proton region, right? So option 2 is satisfying the NMR data. Let's see in the option number 3. So over here you will get a doublet over here, a doublet over here, a doublet over here, and a doublet over here, a doublet over here, and this will give you a triplet, and this will give you a singlet. So you won't get like two doublets, right? So option number 3, you will get a lot of data between 6.8 to 8.5. You will get a triplet as well as a singlet in between this region. So two doublet, along with that will get singlet and triplet as well. So option number 3 can also be not be your correct option. Okay, so that's how you can neglect your option number 3. Option number 2 is the only option which satisfies all the data which are given to you. So option 2 becomes your correct choice for this particular question. Fine. Now let's take the last question of this particular video. So let's take this last question of this particular video. It says that compound P undergoes a pericyclic reaction under a photochemical condition to give compound Q. In compound Q, the relatives to stereochemistry of proton NMR chemical shift values. Okay, so stereochemistry and proton NMR chemical shift you have to tell of the two methyl groups. So I'll just show you that how this particular reaction will proceed. So let me just draw this molecule over here first. So you will be having this molecule something like this. Okay, so just a minute, let me just draw it. Fine. So under HMU condition, it will undergo Kohn rotation, and since it's a 6-pi system, we all know about it. This bond, and this particular bond will take part in that. So this will be done like this. So this will shift over here, this will go over here, and this will come over here. So the product is expected to be this one. Okay. So we expect this to be the final product of this particular compound. So let me just draw it. Okay, so it will look something like this, and both this methyl group will go trans to each other. Okay, you can find it out with the shortcut trick which I have explained you guys in the previous videos. So yeah, it will give you a trans. So both these methyl groups should be trans to each other. The main thing which I want to discuss over here is the chemical shift of it, right? So due to the aromaticity, since it's an aromatic system, right? You can see over here it's aromatic 1, 2, 3, 4, 5, 6, 7. It's a 14 aniline. So now it's an aromatic system. Now in an aromatic system, the inner trans methyl groups will be highly upfilled, okay, because they will be shielded. So they will be shielded, so that's why they will be highly upfilled, and that's why they will give you a chemical shift of -5 ppm. So the correct answer for this will be trans and minus 5 ppm. So this is how this question has to be solved, and this is the correct answer for this. So I hope these were helpful for you. You guys understood how to solve these questions. I just wanted to make sure that every one of you know about how to solve questions from organic spectroscopy. If you like this video, just give it just hit the like button below. And if you are new to this channel and you don't know much about this channel, I'll suggest you to subscribe it, because I usually come across with I usually bring new videos for the preparation of CSIR net as well as GATE chemistry. Okay, so that's all for this video, guys. Thank you so much for watching. Have a great day. Bye bye.